This video is about using and implementing sorting algorithms. So sorting is one of the most fundamental problems that we solve early in computer science education. And the task of sorting is probably obvious, but basically it means that you're rearranging the values in a collection of data into a certain order, generally into some kind of natural ordering like numeric ascending order or alphabetical order for strings or something to that effect, although you can rearrange things into lots of different orders depending on the problem that you're trying to solve. So sorting is not a problem that you have to solve very often today in real-world computer science work, but it's a classic problem, and you can learn a lot about algorithmic thinking by studying it. It's also a problem that can be solved in many different ways, and that makes it a fun problem to teach and fun problem for students to study and learn from. There are a lot of different sorting algorithms out there that all arrange the data in different ways, and some of them are faster than others, and some of them have different memory consumption than others. And some of them are very efficient when you use them with certain kinds of data. For example, maybe it works only with numbers, or it only works with values in a certain range. So there's all kinds of variations to sorting. We're going to look at a few algorithms in this video, one called selection sort and one called merge sort. We're also going to learn what sorting facilities are provided, built in with the Java class libraries. So the first thing is that there are two sorting methods built into Java that are useful. The arrays class and the collections class each have a static method named sort that will sort the elements of an array or a list. So if we go to an editor here and we have an array of elements that is not particularly sorted, if I want to arrange them into sorted order, as long as I've imported the java.util package, I can simply write arrays.sort, and I can pass the array elements as a parameter. And then if I print the array, you'll see that they're in sorted order. So if I want to print the array, recall that I have to say arrays.toString to convert an array into a string that can be printed. So if I compile that and then run that program, you'll see that the elements are now in ascending order. So that's it, arrays.sort. It takes one line of code for any type that Java knows how to compare. So that's very simple and very useful. There's a similar method called collections.sort. So if you have an array list of values and you put some data into there and then you tell it to collections.sort itself, that will give you a list that's arranged in order as well. So those are both very useful, and you don't have to understand the actual internal sorting algorithm that's being used there, although technically I think it's a modified version of an algorithm called the merge sort algorithm that we'll look at in a moment. If you want to implement your own sorting algorithm, that can be useful to learn about as well. So let's talk about one called selection sort. Selection sort is a fairly basic sorting algorithm, and the way it works is that you repeatedly look through the array for the smallest element and then you move it into its proper position. So the first pass you make over the array is to look for the very smallest value, and you move it to index 0. Then you make another pass over the array looking for the second smallest value, and you put that at index 1, and so on. If you repeat this process, eventually you'll have a sorted array. So if we look at the next slide, there are a couple of pictures here. Here's an array of unsorted data. So if we make one pass of selection sort, the idea is that we're going to look through this entire array looking for the very smallest value. Just from eyeballing it, it looks like this -4 is going to be the smallest. And so what we'll do is we will swap that with this 22 here. We'll put the 22 into index 3, and we'll put the -4 at index 0. And the thing that we've accomplished here, after making one pass over the entire array to look for that smallest element, is now we have actually one index of the array that has the proper value stored in it. And if we repeat that process looking for the second smallest element, now that this guy is in place, if we make another walk through the array starting from index 1, I think at this point the smallest element value is the 2. And so we're going to swap the 2 with this 18 here. And so after the second pass of the algorithm, we should end up with 2 here and 18 there. And if we make one more pass, I think the next smallest value is 7 at index 8 here. So I think we will move the 7 to the index 2 of the array and the 12 to its former location. You might wonder, why do we swap them rather than maybe inserting the 7 here and sliding everybody else over? The reason is because it takes a lot less time to swap two values than it takes to shift all of the values over. And the goal here is to try to do sorting quickly and efficiently if we can. So this is an algorithm that is nice to study because it's not particularly difficult to implement compared to some of the other algorithms. It's not the best sorting algorithm in terms of efficiency. Let's look at the code for a moment and maybe we'll see why. So here is a solution to selection sort on an array of integers. And the code isn't too fancy. What we're doing is we're making a series of passes over the array. And each pass starts at some index I and goes up to the second to last element. So, excuse me, each pass is actually represented by this inner loop here, this J loop. And a pass starts, there's some index I that we're looking at. And then for every index j from I plus 1 up to the end of the array, we're looking at each element and we're trying to decide which of those elements is the smallest. And at some point, we will flag a particular element as the minimum one in the array. And once we have finished the end of our loop here, we'll do some kind of swap between index I and index min. So if index I is here and index min happens to be here, we will swap those two values with each other. I'm cheating a little bit here because I'm using a method that I didn't write called swap. So you could assume that we've written such a method that takes an array and two indexes and swaps the two element values stored there. That would just be a couple of lines of code to do that swap. So that's basically the code for selection sort. Not too hard to implement. The big question would be, how efficient is selection sort? How long does it take to run? So the way that you can get an intuition about that is to notice the fact that there are two nested for loops that basically go up to the length of the array, or at least some multiple or some factor of the length of the array. And so that means that you have a loop that's doing something n times, and inside that loop you have a loop that's doing sort of roughly n, or maybe n over 2 times. So you're going to multiply those together roughly if you're going to be talking about the runtime of this overall method, where n is the number of elements in the array that you're sorting. And so the product of those things is some sort of n squared value, maybe 1/2 n squared or something like that. So if you were to actually run this and do a timing test to see how long it took to finish, on one computer this might be the kind of data that you would see. So if you fed it 1,000 elements or 2,000 elements, it runs pretty quickly. So this is a pretty decent algorithm up to a certain input size. But once you start getting up into the 32,000 element range, you start getting these values that are somewhat slow, 600 milliseconds, 2,500 milliseconds. If you look at the difference between these numbers here, once you start getting up into the interesting data range, you start sort of seeing a times 4 multiply here. Roughly speaking, we sort of go from 10,000 to 41,000, 41,000 to 160,000. So we're doubling the input size, and then we get a quadrupling of the runtime, because 2 squared is 4. So that is not a very good result when you look at a big number like 256,000 elements, and it takes us 165 seconds, that's almost 3 minutes to sort an array of that many elements. That's really not acceptable to have it take that long. So selection sort is good to study to understand a sorting algorithm that works correctly, but it's not an algorithm that you would use to sort a really large data set. So let's just briefly look at another algorithm called merge sort. We're not going to look at the code to implement merge sort. That is written up as the case study of this chapter of the Building Java Programs textbook, but maybe we'll talk about the intuitions of the algorithm here in this video. Merge sort is an algorithm that divides the data set in half. It looks at each half separately and tries to sort those halves, and then once it has done that, it tries to take those two sorted half pieces and merge them back together into one large sorted whole. And so the algorithm basically is self-descriptive because it uses sorting on the halves as part of its own overall sorting operation. And so often this algorithm is actually implemented using recursion, as discussed in the previous chapter. So often when you're implementing this method, you will use your own merge sort method to sort the halves that you split the data into in each step of this algorithm. And it's somewhat complicated. It's harder to get this to work, and the code for it is a little bit more confusing to look at. But the reward we're going to get is that this is going to be a much more efficient algorithm. It might not be obvious that that would be the case. Maybe I'll show an example of a picture of this running to help you see how it would work in action. So here's an example of an array with 8 elements that we want to sort with the merge sort algorithm. What we'll do is we will split the array into 2 pieces, and then we're going to process each of those pieces recursively. So here we're going to look at this piece on the left first. We'll again split that into 2 pieces, and first we'll process the one on the left. So we'll again split that into 2 pieces. The algorithm doesn't have anything to do if each piece is only one element. There's nothing to sort. So now the job is to merge those back together into a 2-element chunk that is sorted. So if we have a 22 and an 18, the 18 will come first, and then the 22 will be second. So we'll do the same thing to the right side now, the 12 and the -4. We'll split it apart and we'll merge it back together, and the -4 comes first now. Now we have these 2 chunks, this one and this one, that we're going to merge together into a sorted whole. So now we'll again sort of look at them and figure out which ones come first. The -4 comes first, then the 12, then the 18, then the 22. Now we're going to do the same thing down the right side, splitting, splitting, merging, splitting, merging. And again, this we'll look at these 2 and put them together, the 7, then the 31, then the 42, then the 58. And what this algorithm relies on is the fact that taking 2 things that are sorted and merging them together is not all that hard. Basically, the way you do it is you start at the beginning of each array and you compare those 2 values to each other. You see which one's smaller, and that one you put into the result. And then you move on to the next element of that side that you took from. So now we're comparing 58 to 31. The 31 is smaller, so we'll take it. And now we'll move to the next one. Now we compare 42 to 58. We'll take that. Now we're done over here, so we'll take the 58. So this merging process can actually be done pretty efficiently. And so this is a very smart algorithm for dividing the data up so that it can do it in this way. Once we've got the 2 sorted halves, each with 4 elements, we just do one final merge operation. And now we're left with a sorted whole at the end of the sorting code. And I said that merge sort was faster than selection sort. Well, I'm not sure if I can give you a good intuition in this video for why that's the case. The chapter certainly talks about it. The way that I would try to describe it intuitively is that if you think about the runtime, in the selection sort example, we talked about how we had 2 nested for loops, and each of them did about n things. So I think a way of thinking about it is, you're going to have to walk across all these elements to merge them all together. So you had to do 1, 2, 3, 4 choices here to sort these together, and 5, 6, 7, 8. So you're going to have to do sort of n operations horizontally here in the algorithm. And then if you're thinking vertically here, how many times am I going to have to split this apart and merge it back together? Well, the number of times you have to split the array apart has to do with how many times can I divide it in 2 before I get down to a single element. And if I raise 2 to some power, and that'll give me the overall input size n, this is the number of times I have to split the array apart, then just rearranging this equation, if I say the log base 2 of n, that's the number of times that I have to split this array apart. So basically the height of this algorithm is a logarithm based on log base 2 of n, and the width of this algorithm, if you want to think of it that way, is sort of n. So the overall runtime that this algorithm takes is somewhere in the neighborhood of n times the log of n. And remember that selection sort took something on the order of n squared, or 1/2 n squared. And if n is a really big number, then definitely n log n is smaller than n squared by a wide margin. One way of thinking about it, is if n was equal to 1,000,000, then the log of n, the power that you have to raise 2 to get n, is something in the neighborhood of 20. And so, this would be n times 20 versus n squared. So hopefully you'd believe that this one is a lot better if in terms of you want a smaller runtime, you want a faster runtime for your sort. If you want to see that in a little bit more concrete way, here is an actual runtime graph of a machine running the merge sort algorithm. And what you might notice is the runtime really doesn't start to get long until you have really big data sets. I mean, this is 2 million elements and it does it in 1 second. You might recall that the selection sort graph, we kind of topped out here at 256,000 elements. I'm going to pop that one back up on the screen for a comparison. This is selection sort again. Notice that we have 256,000 elements and it takes us over almost 3 minutes to do that, 164,000 milliseconds for selection sort. And remember that the runtime kind of quadruples every time you double the input size. For that same number of elements, 256,000 elements, with merge sort, we're only up to 125 milliseconds as opposed to 164,000 milliseconds. So merge sort is much, much, much faster than selection sort when given the same amount of data. And actually, if you look at the jump between the adjacent numbers, when we double the input size, the runtime seems to go up by slightly more than double rather than times 4, and that has to do with the n log n instead of n squared runtime class of this algorithm. So a modified version of merge sort is what Java is using internally in its own sorting methods like arrays.sort and collections.sort. Obviously, this one's a lot better performer than the selection sort algorithm.